Yes. If you tell me literally at 12:33, I will remember.
Oh, exactly.
Somebody will be in here texting. But literally, like Marion came up right before lunch. Remember record? I was like, no. But if you tell me right before I start, I'll remember. Sorry, I know my weaknesses. But yes, I'll be happy to if you give me a quick reminder. All right, so we are going to jump. What I was going to cover for all of this chapter typically is we start out with the basic functions, which you may or may not have done with Homer's last year. You did do some of those. We've learned a lot more, like we have basic log functions, exponential functions, different things too. I'm going to skip that for now. Not saying it wouldn't be helpful, but I'm saying there's a greater likelihood that you're going to see a rational function question on this state test than this. So I'm going to skip the family of function stuff. And I'm going to skip over that for now. I'm going to skip all the shift, reflection, stretch stuff for now. Blah, 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 blah. All that domain, range, symmetry, all those things are great things. We'll learn it eventually. But for now, we're moving past that to rational functions. Okay? So rational functions are functions that instead of, you know how a polynomial could be something technically as simple as, I don't know if you know that, but a polynomial could be something as simple as y equals 1, y equals x plus 1, y equals x squared plus x plus 1, y equals x cubed plus x squared plus x plus 1. It could keep getting bigger and bigger and bigger, higher and higher powers. The only condition on a polynomial function is that a polynomial function has exponents that are positive integers or whole numbers. No negative exponents, because a negative exponent would flip that x and put it in the denominator. And if an x shows up in the denominator like that, it becomes, in many cases, a rational function. So a rational function essentially is a function that has some version of a polynomial on the top, some version of a polynomial on the bottom. Okay? Now, I think you'll like this stuff. It's not hard. It's very fact-based. Those of you that can learn little rules and little definitions, it's not like you have to think outside the box on this. It's just, do I learn it? Do I know it? Boom, and you can get stuff. Very rarely do you have to go, that's tricky. I mean, it's information processing it. But that would be an example of a rational function, a really ugly version. But it normally looks like a polynomial over a polynomial. Now, again, sometimes we say poly, it means more than one. But by definition of a polynomial is anything right there. That's kind of a polynomial definition where the n's are whole numbers. But I could make n 0, and a lot of this stuff cancels out, and I'm left with just a constant. All right, so it could, by definition, be a really small number. So where did I go? Oh. Okay, so what I want you to understand is that rational functions are essentially fractional equations. Fractions represent things. So I want you to think with me for a second. What if I told you, and this is going to help you think about what a rational function would look like, okay? Doesn't mean it's exactly this, but it's kind of this. So what if I told you that I had in my pocket 21/5 dollars. Now, what did you do in your head to process that real quickly? You divided, right? And when you divide, you get $4-ish, right? So I have about $4. About. Now I have exactly 4 1/5 dollars. But I have about 4. So if I ever want to know about what a graph looks like for instance, this thing, I'm willing to bet that right this second, when you look at f of x equals 3x squared minus 5x minus 2 over x minus 3, you have absolutely no idea what it looks like. That's my guess. Maybe for the split second before your brain kicked into gear, when I say I have 21/5 dollars, you don't know immediately until you divide, right? Like if I give you some really, you're like, what is that? And you do the division, you go, oh, that's about 4. Well, the same thing is true for rational functions. If I want to have an idea about it what it looks like, all I have to do is take that denominator and divide it in the numerator and ignore the remainder. And that will tell me when I do that about what this graph is doing. Now, again, I have $4.20, right? 4 1/5 dollars. Dividing, you have to be careful and understand what you're doing. When we learned to divide, we completed it all the way down to a remainder. What this graph actually is the same thing as 3x plus 4 plus 10 over the x minus 3. This right here and this right here are the exact same equation, just like 21 fifths is exactly 4 1/5. Are you seeing that? But right here, I think it's a little bit easier to look at that and go, wait, if y equals that, then y equals that. This is going to look a lot like a line. The line 3x plus y equals 3x plus 4. Now, is this stuff doing something to it? Yes, it's affecting it. It's throwing a big vertical asymptote in there. And you can see that. I even gave you a picture of it on the back side. If I were to graph this equation, what we would see if I went out to like -30 and +30, and I could graph the original one or the one divided with the remainder over the divisor. If I graph them, you see these blue looking, they almost look like a hyperbola or something. They're not, but they kind of look like that. But as I zoom out further and further, -60 to 60, -180 to +180, as I get further and further away, what do you start noticing? What do you start noticing as I get further and further away? It kind of just looks like a line. Now, this part right here is following the vertical asymptote. You can't really see it there because it's right on top of the y-axis. It's still there, but what you can see is the graph kind of resembles the line. The graph kind of resembles the line. What was it? Y equals 3x minus something. What was it? 3x plus 4. It kind of looks like the line y equals 3x plus 4, but it's not. It's following it. But again, $4 is not what I have when I have 21 fifths, but it's about what I have. So if you ever want that general look of what a equation looks like, or what it's following to all eternity, just divide and ignore the remainder. And when you divide and you ignore the remainder, when you do that, you get some kind of asymptote that the graph is following. This particular one, when we divide and ignore the remainder, like right here, we're finished dividing. If I were to take this and just completely ignore the 10 over the x minus 3, this is what I call a slant asymptote. And why is it called a slant asymptote? Because it's slanted. That's it. If it ever had no slant to it, like what if I got f of x equals 5 plus some junk? I throw the junk away and I get f of x equals 5 or y equals 5. What does y equal 5 look like? It's a horizontal line, right? Not slanted, it's horizontal. I would call that a horizontal asymptote. Sometimes I get horizontal asymptotes that are like y equals 4, sometimes y equals 0, sometimes y equals -3. That means if I zoomed out on this graph, what would the graph be doing for all eternity? It would be following that asymptote. Now, believe it or not, sometimes they're not linear. Like, think about it. What if I were to divide an x, and what if that numerator, instead of being x, what if it was something like x cubed and 5x squared minus 2x plus 4? What happens right here? I end up getting some quadratic. Are you following me? Well, sometimes the behavior of the graph for all eternity will look like a parabola, which means, and listen, the graph might not do that. I mean, it just might resemble this. So literally your graph might be following this along like this up for eternity. It might be following this one to eternity, but somewhere in the graph, there might be this vertical asymptote that's messing with it right as it gets really close. It's possible the graph looks like that. And if I looked in really close, like at -10 to 10, very few people would look at this and go, oh, parabola. But as I zoom out and out and out and out, that behavior forever to the right and forever to the left over all eternity, you get that behavior by literally taking the denominator, dividing it into the numerator, and tossing the remainder. All right, just throw it out. And when I throw it out and the divisor, when I do that, this asymptote, sometimes it's curved, although we're not going to graph any curved ones. Ours are all going to be horizontals or slants. But that asymptote gives me that infinite behavior forever to the right and to the left. Are y'all seeing this? And that gives us an ability to have an idea about what the heck this thing looks like. Because right now, other than plotting points, I've got no idea. I mean, none, other than this information I have. I mean, I can eyeball it and go, yeah, x goes into that something x times 3x times. So it's a slope of 3. But I would have to do the division to figure out exactly what that is. So if I ever ask you for a slant asymptote, all you got to do is take the denominator, divide it into the numerator. And if I end up with a line with a slope, it's a slant asymptote. Now, if I don't end up with a line with the slope, and instead I end up with like y equals 4, y equals 0, something like that, well, we call those what? Horizontal asymptotes. And yes, you will have a couple problems where I might ask you on a test, what kind of asymptote? Like right here, if this was cubed and that was squared, and you look down here and you go, well, this is a power of 1, and that's a power of 3. Really clearly, when I divide an x into an x cubed, I get a what? X squared. That would be a parabolic asymptote. Most books, once you get beyond slants, which are x to the first, and you start running into x squared asymptotes, which are parabolas, or x cubed asymptotes, they just kind of lump all those together and call them oblique asymptotes. But I can tell you, last year, the year before, I went online and went through books, and I found very little consensus about that. Some people called every asymptote an oblique asymptote, whether it was slant or horizontal. Some people called, oh, just x cubes are higher. So really, I'm not going to quibble about all that. I tend to call oblique asymptotes those higher powered ones. And then I just say slant or horizontal for the ones we use a lot. Sometimes I might call a x squared one a parabolic one or a quadratic one. But I'm not going to quibble about that kind of stuff. But I will ask you to find them. And remember, when you find them, do not count the remainder, which makes it really easy to divide. I mean, look, x into that, 3x times, multiply, subtract. X into 4x, 4. You don't have to do anything else here, because the second you hit your constant, put a y in front of it so it's an actual line, and you're done. That's your slant asymptote. And when it comes to graphing it, you can take that y equals 3x plus 4, come in here, go up 4, mark a point, and do your rise 3, run 3, and you can put a dotted line, and you can go, all right, I may not know much else about this graph at this point, but I do know that as I move forever to the left, it's going to follow an asymptote. As I move forever to the right, it's going to follow that asymptote. May do some weird stuff in the middle. We'll work on that today, but that I know. Are y'all with me so far? Okay, one other thing. I want to debunk something that most of you probably in here think. You probably have heard at some point that you cannot cross an asymptote. Anybody heard that? I'm hearing some yeses. Some people are like, I don't know what an asymptote is. But anyway, you have maybe learned about vertical asymptotes, and you cannot cross vertical asymptotes. You cannot. Why? Because they are where the graph is undefined. Okay? Like for instance, this graph has a, if I plug in 3 in there, what happens in the denominator? And I can't have a 0 on the bottom. If I look down and I see a denominator, and I can tell what value would go in there and give me a 0, that's going to represent a vertical asymptote or something else we call a hole. Talk about holes today too. Those, you cannot exist there. So I'll talk about VAs in a second. A vertical asymptote, yes, you were going to draw a dotted line representing that. This is how asymptotes behave. As you near an asymptote, you don't just get to it, hop over it, and move to the other side. Those are called holes, okay? And we show those by just an open circle. Really, you would never even notice them if you used your calculator, because an open circle is so tiny you can't see it in one little spot. But we represent it as just a big open circle, okay? An asymptote, as you near it, the graph makes a choice to go up or go down. If it's a slant asymptote, as I head there, I will write it from the top, maybe or the bottom, and I will write it out the other way from the top and the bottom. It will follow it out both ways. Horizontals, the graph might be cruising along. As it gets near to it, it'll flatten out and follow it out. That's a behavior that asymptotes have. But you are able to cross horizontals. You are able to cross slants or any oblique. It is totally possible. Might not happen. The general rule is, as you move further and further out, you have less chance to cross. But here in the middle, when I talk about the middle, you'll kind of know what I mean. The graphable part, all kinds of craziness ensues. So you might cross. There are some curves that follow cross an asymptote an infinite number of times. Some weird sine functions and cosine functions. But for the most part, as I move to infinity, the graph kind of settles in on the top or settles in on the bottom and follows it out, whether it's a slant or a horizontal. Are you seeing that? But verticals, you are not allowed to cross. And holes you'll see are just points that don't exist. You go in one side and out the other. So hopefully you can do these real quickly. By the way, I just showed you this table. I showed you the original function. That's the original one I gave you. And then I showed you the slant asymptote. And you can see with really small values like 5, when I plug a 5 in there, a 5 in there, look, my y values are totally different. These aren't even near each other. But as I move further and further out, like 10, 35, 3/7, 34, that's closer. 64.6-ish, 64, 154-ish, 154, 304, 304, 3004. I'm getting closer and closer, right? So you can see the further I go out, the closer the real graph is to the asymptote, which is the whole general nature. Because you will not even notice a difference if you move way, way out to something like x equals 1,000. And you would notice the same thing if I went left as well. Now, there are some weird graphs that actually have one asymptote one way and then a different asymptote the other way. There are some that have a slant one way and a horizontal the other way. And we're not going to get into those in this class because they're not rational functions. They might be square root functions or other weird kinds of functions, absolute value functions that you might see in calculus or in pre-calc. All right, so let me just give you a little practice with these. This question says, find the slant, the horizontal, or the parabolic. Now, I want you to notice a couple things. First thing, if I want to know any of these asymptotes, what was the thing we did? Long division. Or if it's just the power of 1, what could I do? I did long on the other one because sometimes you have to do long, like here on number 3. If you want to do synthetic, knock yourself out. It works great. Just don't forget about what happens when you have a lead number like a 2. Remember how you have to go back and divide by 2? As a class, y'all did a pretty good job of remembering that this year, but some of you are still forgetting. But right here, I can take that positive 1. I can take positive 1, divide it into 2, negative 3, 5. So here we go. Drop the 2. 1 times 2 is 2. Add that, a negative 1. I can stop right there. I don't even have to go any further because what am I finding when I go further? The remainder, which I don't even care about. So I just put an x right there, set it equal to y. This is a slanted line, so I have a slant asymptote. You with me? All right, look at the next one. I got a 2x minus 1. What do I do on something like that? We factor out the 2. Somebody factored out a 2 on their test and just wrote x minus 1. Remember, when I take that out, I get x minus what? 1/2. So what am I using as my divisor? 1/2. And I'm dividing into 4, 4, negative 6, 10, 8. So I'm dropping the 4. Half of the 4 is 2. Combine. Half of that's negative 2. Combine. Don't even care, do I? Don't even care about the remainder. But I do have to remember to go back and do what? Divide each of these numbers by 2. Set it equal to y, x squared x plus. So I get y equals 2x squared minus 2x plus 4. So in this case, that's certainly not a line, right? So it's not slanted or horizontal. This would be called you could call it a parabolic. What do I call it here? Yeah, parabolic asymptote. I wouldn't care if you called it oblique because a lot of people do call anything that's not linear oblique. But whatever. This means that this ugly function, if you were to graph it, might have some crazy business going on there, around the origin in this area, but as you went further and further out, it's going to resemble this parabola. Are y'all tracking with me? That's what it would resemble. Never land on it. Well, it might cross it, but it would not be the parabola. It's just going to get closer and closer and closer and closer to it as you move out to negative and positive infinity. All right, and then this one, number 3, I can't really do synthetic on that at all, but I want to show you a trick that's going to occur from this. So you would pull out your long division, right? 2x cubed. There's no x squared term, so I'm going to plug that in there, right? Minus 2x plus 1, and I'm dividing that into this. So 2x cubed times what gives me 6x cubed? 3. Sounds like I'm done. I got my constant. So all I do is go y equals 3. Now, doesn't it seem like there might be an easier way to go about getting a horizontal asymptote? Where did that 3 come from, ultimately? These two numbers, right? Which I can clearly see right here. When do you think when I divide, I'm not even going to have an x term? When they have the same power? Memorize that. When my powers are the same, I don't have to do the long division. When my powers are the same, I know that I have a horizontal asymptote. And that horizontal asymptote is y equals the coefficient over the coefficient. So literally, all you have to do is say, oh, look, same powers, y equals 6 over 2, which means y equals 3. And you don't have to do any of that. Are y'all seeing that? Well, let's go one step further then. What if this was my function? Call this number 4. I'll put a, it doesn't matter, a 7 up here. Let's check the division out this time. X cubed, I heard it, minus 2x squared plus 5x plus 2. We're dividing that into 7x squared minus 5x plus 1. What times x cubed gives me that? And remember, I don't want anything like 7 over x or whatever. That'd be it, right? But that's like getting into decimals. Those are like polynomial decimals. I don't want that. So it doesn't, right? Notice right here, when I divide 2x cubed into this, it went 3 times. That was a constant. At this point, this power is less than this, isn't it? Right? I don't want to write 7 over x. Think about it. Polynomials kind of decrease like this. Constant. Technically, 1 over x squared, those are almost like the decimals of a problem. I don't want those. I just want to stop at the constant. Well, if this power is already bigger than that power, it does not go any times. And if it doesn't go, that makes for a pretty easy horizontal asymptote, doesn't it? So what's your second rule for horizontal asymptotes? If the power on the bottom is bigger than the power on the top, you're done. Y equals 0. Horizontal asymptote. Are you with me on that? So the only time you don't have a horizontal is when your power is bigger on the top. That requires you to do the division. And when you do that in this class, or really, honestly, anything in pre-cal, algebra 2, comprehensive math, pretty much you're dealing with slant asymptotes. I don't really have a memory of a math tournament that asked about other oblique asymptotes or stuff like that. Maybe, but I don't have an active memory about it. So anyway, with that in store, let me just give you some good notes about how to analyze these graphs. Because what we're going to do is break these things down by factoring. In fact, most of the time I factor it for you, kind of like I do right here. And we're going to learn about what these things actually mean to you. Okay, so the first thing is, what did we just learn about this graph and slants or horizontal asymptotes? What would you say this has? A horizontal at what? So what is your horizontal asymptote? Y equals 2. Why? Because look, these powers are the same. So I take the coefficient over the coefficient, y equals 2. Now, if I didn't have it written like this, can't you still tell that those powers would have been the same if you FOILed it all out? Right? This would have been an x cubed times 2, 2x cubed. And this would have been an x cubed. So can y'all see that? Even if I had it factored, a 2x cubed over an x cubed, same power, y equals 2. So you immediately know that the horizontal asymptote, and this is the rules on horizontals, would have had would be a y equals 2. Now, I wrote them again for you. So if you forget this somehow before tomorrow, before tonight or whatever, look, if the n, that's on the bottom, if the n is biggest, you always get a y equals 0 horizontal. By the way, don't say 0. Always say y equals 0 because it's a line. If the powers are the same, you always get a y equals top over bottom, a y equals a over b line. But those horizontals to find them. But if the power on the top is bigger, then you do not get a horizontal. You get a slant asymptote, which we've already talked about, and you just go and do the long division. But remember, when you do the long division, what do you do with the remainder and the divisor? You just toss it and ignore it. Okay? Now, jump back. One of the things I like to do before I even get to the other stuff is to look for holes. Now, holes are places in the graph that don't exist, but don't affect the behavior. Now, last time I checked, the only time something wouldn't affect something is if it was not there. Technically, if you look at this fraction right here, I could cancel out the x minus 2's, couldn't I? And since I'm canceling them out, now they're not there, and they're not affecting this graph's behavior. However, they still are a part of the original function, aren't they? That's in there somewhere. Whenever you see a factor in the numerator, the denominator, that cancels completely, you just found the x value of a hole. It's a place in the graph that the graph is curving along and there's just no value there. But the unique thing about it, it doesn't act like a vertical asymptote, which draws the graph downward or upward. It just goes in one side of the hole and out the other. But I want to know where the hole is. So I'm canceling that. But what would the x coordinate be if it's x minus 2? Take a guess. 2. So the x coordinate of my hole is 2. So what you do when you see that, you cancel them out and don't look at them again. But I still want to know where the hole is. I can't say there's a hole at x equal 2. That would be a vertical line, x equals 2. I want to know where is the hole. So how would I find the y value of the hole? Well, I don't have the graph. Plug it back in. Now, am I going to have any luck plugging it back in here? No. No, why? Because those two things are still in there. Are you seeing that? Look, if I plug 2 in there, 8 minus 4 is 4. 4 minus 8 is negative 4 plus 4 is 0. I'm going to get a 0 on the top. What do I do with that? However, if I plug the 2 back in here, after canceling that out, I get what? 2 times a 3 times a negative 1 over 4 times a 1. And what do I end up with? Negative 3 halves. So my hole ends up being 2 comma negative 3 halves. Now, why is a hole helpful? Well, it is kind of a point. I can go to my graph and go over to positive 2, down to 1.5, and I just put a hole there. My graph has to go through that hole. So you're actually finding a point on the curve, but it's a point that doesn't exist. Are you with me on that? Okay. Now, sometimes you have more than one hole. But guys, cancel them out. Never look at them again. You do need to get the x value out of it. Y'all awake? Okay. Check it. I got some weavy heads in here. So make sure you plug it back in and check. And tonight, when you forget all about this and you're like, man, I don't take notes. Who does that? Mostly A students. But if you have a need to go back and look, right here, holes. After factoring the numerator and the denominator, after factoring, if there is a common factor, this will indicate there's a hole. A hole does not act like a vertical asymptote. It's just a missing point. How do you find the hole? Set the cancel factor equal to 0. If I set that equal to 0, I get a 2. So set the cancel factor equal to 0 to get this. Then to get the x coordinate, then plug the x value back into the uncanceled part. So So I'm giving you good notes if you forget that kind of stuff. Sometimes you'll have more than one hole. But guess what happens when you don't do the holes first? These denominators will all of a sudden suddenly look like vertical asymptotes, and these numerators will all look like x-intercepts. You're about to learn that second. Okay, we don't want to confuse those. All right, this thing has 2 vertical asymptotes, 2 x-intercepts, 1 hole. If I don't cancel that out and get it out of the way, I'm going to confuse it with my other rules, and you'll see those in a second. So I'm scrolling up to vertical asymptotes. Now, once you've gotten rid of these holes, you want to knock your VAs out right away. Super easy to do. How do I get my VAs? All I have to do to get a vertical asymptote is take what is left of the denominator, set those equal to 0, and you're done. So if I had x minus 2 under there, set x minus 2 equal to 0, solve, and I get x equals 2. That's a vertical line that acts like a vertical asymptote. If I have a factor in the bottom that's 2x minus 1, set it equal to 0, add the 1 divided by 2, I get x equals a half. There's a vertical asymptote at x equals a half. I always put dotted lines for my asymptotes because dotted lines mean they're not there. Solid lines means it's part of the graph. So dotted lines. But that's it. But look what happens. If I didn't cancel out that hole first, I would be tempted to think VA, VA, VA. And if I put 3 VAs in there when there's only supposed to be 2, that's going to confuse me when I start trying to sketch this thing. That's why I always deal with holes first. Are you with me on that? All right, last couple things you need to know, and then we'll do a couple of these. After VAs, x-intercepts. I can do it the easy way or the hard way, but I'm going to show you the easy way. Technically, an x-intercept is where what? Where y equals 0. So let's just say I had this function, and you had something really ugly on the top and really ugly on the bottom. Technically, the x-intercept is where the y is 0. So I could plug a big 0 in here. Now, how do you solve an equation that's a fraction like this? What would be your first step? I mean, I don't tend to love denominators. Well, that's ultimately what you're doing. But just to show you the y, couldn't you cross multiply? I mean, if I get something like this, if I cross multiply, though, or multiply both sides by the denominator, doesn't this denominator, when you multiply 0, just go away? So all you have left is the numerator equal to 0, right? So if you think about it, rather than overthinking this, that going back to this original problem right here, back to this. So these represent where the holes are. I'm going to get rid of those quickly. These represent the vertical asymptotes right there. Well, anything left in the numerator that has an x in it, set those equal to 0, and you get your x-intercepts. So if I solve for that, I get x equals -1, and I already know the y is 0. Here, if I solve for x, I get x equals 3, and I already know the y is 0. Those are my x-intercepts, right? And the y-intercepts are probably the easiest things. First of all, it's a function. So how many y-intercepts could I have? Only could have 1, right? If I had 2, wouldn't pass the vertical line test. But the y-intercepts, I love it when I give you the function like this, because a y-intercept means when x is 0. So what happens if I gave it to you like this? What is the y-intercept? Well, when x is 0, everything with an x in it goes away, and you're left with what? So the y-intercept is when x is 0, y is 3. Now, it's a little bit trickier if it's factored, because if I plug in x equals 0 in there, all the x's go away, and I'd have to multiply this out. But 2 times 1 is 2, times a 6 is 12 on the top. What do I get? Positive 4 on the bottom, and then I simplify, and I get that 3. Now, we're going to put all this together, but here's the goal. After graphing all this stuff, and maybe if we need it, plotting a couple extra points, I will have a really good idea of where this graph is, how this graph is behaving, and I can sketch it. And in calculus, we'll learn other things like concavity or increasing and decreasing, and we'll use the derivatives to even, we can really, it's amazing the kind of curves we can sketch in calculus without a calculator, just by applying a little bit of Isaac Newton's genius. So I'm going to put all this together with you in the next 10 minutes, and then your job tonight is to maybe work a little bit on some of this homework stuff that you see. And the homework stuff you'll see like, you know, heck, even if you don't work on much on homework. You can maybe finish up this classwork page. But let me just show you this classwork starting out. So I have this function. It's not factored. I really need it factored. So that will be my first order of business. I'm going to go ahead and do that for you. And I factor the numerator, and I get x minus 7, x plus 2. And I factor the denominator, and I get x plus 1, x plus 2. And the order doesn't matter. What do you immediately see right there? We got some holes we need to take care of. So I know that there is a hole at what x value? -2. The second you write down that -2, you're going to scribble that out, and you're never going to look at it again. It does not affect any other characteristic of your graph. Truly, don't look at it again. Now, how do I find the y-coordinate of that hole? Plug that back into what's left, and that gives me a -9 over a -1, which is 9. So there's a hole at -2, 9. I could even go and plot that. I'm going to put it up there, even though it's off my graph. That would be about where -2, 9 is. Are you with me so far? Okay, next thing. Are there any vertical asymptotes? Where do I find those? That's kind of easy to remember because verticals you're not allowed to cross. That would be where it's undefined. Holes are undefined too, but all that's in the denominator. So what would my VA be? And we write that as x equal -1 because that means it's a vertical line. Don't just say -1. Well, look, I can come. I'm going to do that in red. I'm going to go to x at -1, and I'm going to draw a dotted line representing that. I know a lot of people like to bring in colored markers in here. That might help your graphs, help you see stuff, because sometimes it's hard to see a pencil over these lines. So I've got that marked in there. All right, now, what about horizontal asymptotes? Does this have a horizontal? Yeah. Yes, because the power is not bigger on the top. What is the horizontal since the powers are the same? Y equals 1 over 1. So the horizontal, y equal 1. What does y equal 1 look like? Like that. Now, last thing, slant asymptote. Can you have a slant and a horizontal? No, you can only have one or the other. So if I have a horizontal, then I don't have a slant. Now, this one says find the x-intercepts. Are there any x-intercepts? Yeah, right? X-intercepts are found by looking where the numerator would be 0. Where would that happen? It's 7. Now, if you wrote x equals 7, I'd probably be fine with it. But really, it's a point, not x equals 7 looks like a line. It's the point when y is 0, x is 7. So I go out 7, and I mark that point on the x-axis. Can I find a y-intercept? Yeah, that's when what? When x is 0. And look, if I plug in x is 0, all that junk goes away except that. Or this goes away except that. And I get what? -7. So at 0, -7, I've also got a point. Are you all with me? So this last part, which we're going to actually learn to do better than this, but this last part says, hey, just to make sure, plot a couple extra points. On your test, so right here, I said plot a couple or 1 point on either side of the VA. What I'll probably do on your test is give you a little chart, and I'll give you a couple x values like, hey, what goes with -5? Hey, what goes with +3? And maybe I'll ask you that. So you can come back and look, you can use this part right here. You don't have to use the original equation if you've canceled out a hole. If I plug in -5 in there, I get what? -12 over -4, which is 3. So that gives me another point. At -5, I'm up here at 3. And then if I plug a 3 in there, I get what? -4 over 4, which is -1. So that tells me at 3, I'm at -1. Now, here's where you put all this together. What do you know about horizontal asymptotes? What does the graph have to do with horizontals and slants? You spent like 10 minutes on this. Some of y'all are waiting for somebody else to talk. Think. It's got what? It's got to follow it. So when I'm graphing, guys, you ever take a multiple choice test and you don't know the answer, but you know it ain't A, B, and D? And you're like, I don't even know what the word in C means, but I know it's not A, B, and D. You go with C and you get it, right? Because you're good test takers. That's how you're going to have to think when you're sketching these. It's not so much that you're going to look at this information all the time and know what to do, but you're going to be able to eliminate what not to do. And the result is going to give you where you're going. Now, if I know with certainty that a horizontal graph, it follows it out to the right for, like it follows this forever, then think backwards. I'm coming in from forever and I'm right on this horizontal, right? What do you think that graph does as it gets closer in? It's got to go through these points, doesn't it? It has no choice. It's a point on the curve. It can't just go up and go, I'm not going to do those points. They're points on the graph. So it has to come in here and it has to cross there, hit there, and go down. Now, I will say that it's going to do that a lot more smoothly than I just drew it. But I'm not going to count off and do this. This thing really is very smooth about its progress. Very smooth when it does this. Now, how did I know that it went down there? Why couldn't I have hit this y-intercept, turned, and headed upward? Somebody give me a reason. To go up, it would have had to cross what? The x-axis. Can it cross the x-axis there? You just said the only x-intercept it had was at 7. There are no other x-intercepts. This is not a suggestion. This is not like, okay, I'll give you one, but that's it. The other ones are super secret and hidden. No, that's it. So I can't do it. I can't go back up. I have no choice but to follow this estimate. Also, why can't I cross over the vertical and just connect in with that point? You can't cross verticals. I can cross horizontals. I can cross slants, but I never can cross verticals. So that's the only thing on the right side. Now, what's on the left? What does it have to do? It has to go over the hole. It has to hit the hole. It has to hit the point, but it also has to follow the asymptote out from infinity. So come in from negative infinity. Come in from negative infinity. What do you think it's doing as I'm coming in? You think it's going to go down? Tell me why it's not going down. First of all, it has to hit these points, right? What if those points, what if you didn't see them? How would I know that it's not going down? It would have to hit the x-axis. And to hit the x-axis would mean there's an x-intercept there and there's not. This has no choice but to go, well, since I can't cross, maybe I'll just head the other way, which makes perfectly good sense with this point and this hole. Why can't I hit this hole, turn around and come down? Because it would hit that, right? And I can't hit that. Right? So I have no choice but to follow that vertical up and that vertical down. Are you tracking with me? Here's what I want you to do tonight. I'm going to make it easy on you. Just do this and see what you can do. Oh, and one other thing I want to talk about. The last little thing. If you see a squared there, this squared is on a factor that will give you an x-intercept, right? Because it's in the numerator. What do you think that does to the graph? Instead of crossing at 1, what's it going to do? Bounce at 1. So it's going to cross. Actually, it's not crossing at -2 because that's a what? Hole. It's going to bounce at 1 and it's going to cross at 4. Now, last thing. If in the denominator you see a squared, or any even, by the way, that represents the VAs, doesn't it? You know what this does? Do you remember the 1 over x squared graph? What was the 1 over x squared graph? Do you remember? The volcano? Any factor in the denominator that's squared, instead of the graph following it like this, like it did on the last graph on the vertical, it does a volcano up or a volcano down. We won't really know until we start sketching this. So that tells me here, oh, this thing's going to do like this, or it's going to do like that. Can't do both, but it's going to do something like that because it's squared. So do the best you can on this. If you screw it up, don't worry about it. We're going to do all of this again tomorrow and finish it up on Friday. And really, there's not anything really new to it. It's just exposing you to new stuff. I can't say there's nothing, but there's nothing that you're going to readily look at and know. So there are certainly things that might affect that, like are there other factors? Are there other VAs? Are there holes? But nothing that it's worth not making a note of. Y'all have a good one. What's up, guys? How's the day going? Not too bad.
I'm working soccer today.
Oh yeah?
Soccer, yeah.
How are they looking this year? Y'all are always good.
We won our first. We beat Phone 9-0, and yesterday we beat Trust Roll 5-0. We're doing good so far.
Nice.
I
JB, Varsity, what are you playing?
JB.
JB?
Mine was probably pretty good, and we're at there.
Yeah.
Hopefully it goes good.
Does the home field advantage make that much difference in soccer? I would think it makes a lot less than like basketball or something.
It makes a little bit of a difference because you're used to playing when you're in the field.
That's true.
At this point, everyone in our team has played at that field at Bhutan. It doesn't make time.
Yeah.
It's better to be at home.
Oh, no doubt. So, who is that? Libby D. What is that? Literally, I almost said, I'll text her and let her know. Can't do that, can you? That.
Sorry, I didn't know that I wasn't on the show yesterday, so like, good morning.
No worries. Thanks for making that test up too.
25.
I was like, how would I
Eerie.
Go to school.
Always those jelly and being.
You can just tell you next week. Okay, I don't feel like I'm just moving this. Okay. I'll be my hands.
Oh.
I don't think it's bad.
Like,
I have just like what's like I'm not trying to miss a day.
yeah.
I'm feeling so inspired.
That's you do that.
All right, guys, y'all ready?
I was born ready, sorry.
That's what I like to hear. Can y'all sit so I can tell who all is here? 3, 4, 1, 2. Jackson. Switching again. Okay. No band. Yes. Okay. All right. All right. Okay, guys, remember we're stepping away from that state test, but remember on Friday, we're going to talk about test G 1 through 25. So if you didn't work on it, make sure you work on that before you come in here on Friday. But we're going to jump and start talking a little about rational functions. Now, rational functions, we're going to have a whole chapter on basic functions and rational functions. So make sure that you don't discount this or just be like, oh, it doesn't really matter, because you're going to have a test over all this. And we're going to kind of officially begin this chapter the Monday. Well, I guess we're officially starting it now, but we're going to incorporate all of this with the other stuff the Monday after our state tournament. So in a couple Mondays. So jump right now to, I think it's page 79. So we're skipping over the stuff right before that. It has to do with basic functions. All right, so page 79. I think it's my 79. Is it y'all 79? 75 looks like that. Okay, you're 75. This must be, yeah, this is an updated one. I added some junk in there. Okay, so the first thing I'm going to talk about are what a rational function is. Everybody with me? Okay, so we just got finished with polynomials. All right, now we didn't talk a lot about the behavior of polynomials in Algebra 2. That's something we tend to talk about as we move forward into pre-cal, things like that. But a polynomial is defined like this. So on page 75, a polynomial function is defined as something that has a bunch of parts, potentially. And basically what this means is it has some coefficient with x to a power, another coefficient with x to 1 smaller power, another coefficient with x to 1 smaller power, all the way down to a constant. But technically, if all of your coefficients were zeros, you could end up with a really small term, like something as simple as a linear, something as simple as a horizontal line, something as simple as a parabola. Any of these are technically polynomials. And I know that's a little sketchy because poly means more than one term. But by definition, all of these would resemble this, because the key to a polynomial is that your exponents are whole numbers. Cannot have fractions as exponents, cannot have negatives as exponents, or decimals, just whole numbers. Because if you had decimals, it creates roots. Those aren't polynomials. And if it had negative exponents, those create denominators and turn them into rational functions. So what we're talking about, a rational function being, is basically a polynomial over a polynomial. That's it. Now, there are behaviors about these that we want to talk about, because it's really easy to sketch a line. It's not too bad to sketch a parabola. It gets a little trickier to sketch cubic functions and things like that. But we're going to want to be able to sketch and interpret what these rational functions look like. And there's a whole lot of easy questions we're going to get out of this, like, does this function, polynomial function, or I'm sorry, does this rational function have a hole? Does it have a vertical asymptote? Does it have a slant asymptote? Does it have a horizontal asymptote? All these kinds of things we can learn with just a little bit of looking into these. So the first thing I want to talk about and we're going to put all the other stuff into it in a second, is when you stare at a rational function, and again, polynomial, it's a parabola, over a line. What would this thing look like? Now, there are all kinds of itty-bitty details on this particular function that we're going to have to consider, like x-intercepts, y-intercepts, vertical asymptotes, whatever. All of those things control the behavior when you are dealing with really small values of x. Kind of like if you were graphing something on a graphing calculator, most of the windows go from -10 to 10 when you start out. In that region right there, these are going to behave erratically. But then as the further you move away from the origin, out at x equals 20 and 30 and 50, or -20, -50, -100, the further you move away, this graph starts to resemble something. And what it resembles, you could characterize that as your oblique asymptote. Like I look at this and go, oh yeah, that function is going to look like a line. And how do I know that? Because of this kind of thinking. So what if I told you right now that I had in my pocket 21/5 dollars? Now, the second I wrote that, you just saw a fraction, but it didn't take you long to turn that fraction into what? So you get about $4, right? Now, what do you have exactly? I have exactly $4.01 of a dollar, right? Or $4.20. But I have approximately $4. Well, this function right here, this rational function, I could divide, just like I did here, 5 into 21 is 4 1/5. I could divide x minus 3 into that. And if I did, you can see the long division. I could have used synthetic 2 on this problem. I get 3x plus 4, but I also get what? 10 over the divisor. This right here is the exact same thing as this. Those are the exact same things, just like 4 1/5 is the same thing as 21/5, okay? But the upside of this is I have an idea about what this graph looks like. This graph looks like a line. Now, does it look like a line if I look at a graph from -10 to 10, +10 to 10? No. Or -10 to 10? No. But the further I move out, the more it's going to resemble the line y equals 3x plus 4. And because that line has a slope and it's not a horizontal line, I call that a slant asymptote. Now, to be a slant asymptote, I've got to throw that junk off. Now, if I throw that junk off, no longer is that line the same as this, is it? If I get rid of the remainder part, just like no longer was 4 the same thing as 4 1/5. The slant asymptote gives you a little window, a little insight into what this graph actually looks like. So I'm going to show you this through a couple of little strategies. If I scroll down here, here is the original function. There is the slant asymptote with the remainder thrown away. Look what happens when I plug in values of x that are not that big. My y values end up being very different. But look, as the x values get bigger and bigger and bigger and further away, what do you start noticing about the y values? They're almost exactly the same. What does that mean? That means that this ugly function is getting closer and closer to looking like what? That line. So it never becomes exactly that line. Now, if you were rounding to the tenths or the hundredths, yeah, they would look the same. But it actually is just getting closer and closer and closer and closer, like what an asymptote does. Now, you guys probably haven't dealt with many asymptotes. I think you've talked about a vertical asymptote before, though, haven't you? Maybe at some point. A vertical asymptote has that property when the graph gets closer to it, it's either got to dive downward or dive upward. It can't get to it, hop over to the other side, and continue. That's just not the behavior of an asymptote. Well, we're going to add to vertical asymptotes slanted asymptotes. Well, the graph is still going to have to follow that thing up and follow that thing down. All right? Horizontal asymptotes. The graph's going to have to follow that out to the left and follow it out to the right. Are y'all seeing that? All asymptotes behave that way. But if I want to know what the graph looks like as I move forever to the left and forever to the right for all eternity, all I have to do is to divide the denominator into the numerator, throw the remainder away, set it equal to y, and that's giving me some insight into what this looks like. Let me show you this with a bunch of graphs. Flip to the next page. Here is the first function in blue. All right. Now you also see that little diagonal line. That is the slant asymptote. So if I graphed the original function, all I would see is this blue thing. And if you looked at this blue thing, what would you describe this as? Most people are like, oh, a couple of parabolas, which it's not, but it kind of looks like it. Or maybe a kind of a tilted hyperbola. I mean, all kinds of things you might think. But the bottom line is, this is just whatever that rational function is. Looks kind of weird, okay? But look what happens is I change my window and go out to, this is 30 to negative 30, negative 60 to 60, negative 180 to 180, negative 1,000 to 1,000. The further I go out, what does this graph start looking like? Y equals 3x plus 4. Now, does it really, is it 3x plus 4? No. I would just have to zoom. And if you're wondering where the vertical line is, it's there. This graph is still going like this and then going, you don't see the vertical asymptote in there. We'll talk about that later. But there actually is this vertical asymptote. It's going vertically. And the graph is coming down and shooting up and shooting down. But the further I zoom out, all I'm noticing is the line. So if I ever want to know the behavior of a graph, what's it doing to the right and the left? If it's a rational function, do long division or synthetic division, whatever you're capable of doing, toss the remainder. And if you get a slanted line, it's a slant asymptote. It's a slant asymptote. If you get a horizontal line, it's a horizontal asymptote. Every now and then you get a parabola. Well, what would that mean? That just means that you're going to have a really weird looking asymptote, but it is totally possible. Like something like this, and you'll see this in a second. Can you see that if I started the division right here, what's the first thing you get? 2x squared. Now I'd get some other stuff too, right? But can you see that what would my graph essentially look like? A parabola. What that means is, and I'm just doing this loosely, you literally, there is a parabola that is your asymptote. Most people don't think of curves as being asymptotes, but what that means is this graph, if I graphed it, was going to come down like this maybe, and then as it gets closer, there's actually a vertical asymptote in here too, which we'll talk about in a second. And it probably does this, and then it probably shoots up maybe, and then it comes up here and follows it out. And if I were to pull out my calculator and graph it from like negative 10 to 10, you'd probably see this. And most people on the planet would not look at their window and go, oh yeah, parabola. But what happens is I zoom further and further out, I start seeing this big parabola thing. Now, you're not going to be graphing parabolic asymptotes. Anytime the power of your asymptote hits 2 or more, some books just refer to them all as what we call oblique. But I've looked at so many books and so many websites that call oblique different things. Some people call all behavioral asymptotes oblique, like anything slanted or quadratic or anything like that. Some people only refer to as obliques as powers that are like 2 and higher. I don't care. I'm not going to get picky about that. You can call that a parabolic asymptote if you want. But sometimes people refer to the behavioral, the one that determines long-term behavior. They refer to them like this. But we're going to talk a bunch about slants and horizontals. Are y'all with me? Okay. So in a nutshell, that's one of the things that we're going to be finding. And let's talk about actually finding them. And I want you to notice a couple of things. First one, find the slant, the horizontal, the parabolic, whatever it is. So if I want to know how this thing behaves forever and ever, what do? Divide. Now, because this is x and not x squared, let's do some synthetic. I wish y'all like that a little better. So I'm just going to use positive 1. I could have done that in my example too, but positive 1, 2, negative 3, 5. Now watch how easy this is. Drop the 2. 1 times 2 is 2. Combine it, negative 1. Do I really need to go any further? Because I don't even care about the remainder. If I want the slant or horizontal, whatever asymptote, I don't even care. So all I do is put the x in there and set it equal to y. So what does this graph actually look like? A line y equals 2x minus 1. That's it. Now, up close, does it look like that? No. But long term, that's going to tell me what the behavior is as I move to the left and the right. What about this one? Oh, so by the way, I would call this a slant asymptote, if you care about the spelling. I know that's something like isosceles. It's hard to spell. One kid, I asked him, I put on a test once, what's the name of the thing that's slanted? My favorite all-time butchering of asymptote was astropoles. That was hilarious. Anyway, no, they are not astropoles. They are asymptotes. Okay, what about this one? I'm throwing you a little curveball. You can use long division if you want. Some people like the long division, and you'll see long division is not that hard because you only have to do a couple steps. But if you're doing synthetic, what did we have to do here? We had to factor that 2 out, which gave me x minus what? A half. So I synthetically divide with a half. And what do I have to remember to do when I'm finished? Divide by 2. Y'all actually did a really good job comparatively in doing that. But remember, you have to go back and do that. So here we go. 4, -6, 10, and 8. So drop the 4. Half of the 4 is 2. Combine. Half of the -4 is -2. Combine. Do I need to go any further? You can if you want. I know I habitually do, but it doesn't matter. I'm looking for an asymptote. So what 2 things do I have to do? What 3 things do I have to do? 4 things? Divide by 2. Set it equal to y. Put your x squareds and your x's in there. So 2x squared minus 2x plus 4. So what kind of asymptote would that be? Looks like a parabola, a quadratic, a parabolic, oblique, whatever. I'm not going to make us graph any of these on this test, though, or this, whatever we're doing. We're just going to be graphing horizontals and slants. So that you would have to graph. That would not be something I might give you this problem and say, hey, what's the asymptote? And you're done. Okay. All right. Number 3. You got to remember this rule. You're going to come up with it on your own. What's the asymptote here? What are you going to do? I'm going to divide what? I'm going to divide 2x cubed. I'm going to have to do long division here. Plus 0x squared minus 2x plus 1 into 6x cubed minus 4x squared plus 5x minus 1. So first step, what do I get? 3, done. Once I hit a constant, I'm done. Did I have to write all this out to get that? Come up with a rule for me. If the highest powers are the same, then what? Look at it. How did I get a 3? Take the top coefficient and divide it by the bottom coefficient. Set it equal to y. So please, for the love, do not do this. If I look at a problem and somebody says, what kind of asymptotes does it have? If I see the powers on the top and the bottom the same, take the 6 over 2, you get y equals 3. What does the line y equals 3 look like? So that's a horizontal asymptote. And I write these as HAs all the time, but you can write horizontal asymptote out if you want. Now, is that the only horizontal asymptote that occurs? Now, if you've noticed, when I do long division, I'm always doing the long division until I hit the constant, right? And if you look back at this, I was able to do the long division here one step because this power, that 3, was the same as this. But look, if I would have continued this step, wouldn't I have gotten this? Change the signs. Wouldn't I have gotten -4x squared, positive 11x minus 4? Why would I'm going to go back and put this 2x cubed in here. Why here do I not go further? Tell me why. Yeah. For me to say What times this gives me this? The answer to that would be -2 over x, wouldn't it? I don't want to go that far. As soon as that power becomes smaller than that power, I don't divide anymore. So with that little nugget in mind, make this number 4. What would you do if I said this? Here's your function. Say you had 2x squared minus 3x plus 1, and the bottom I have an x minus 5. What happens here when I try long division? Sorry, not this. Make that x cubed on the bottom. What happens here when I try to divide? That's smaller, isn't it? I can't. So how many times does it go in? None. Set it equal to 0. Set it equal to y. Couldn't we come up with a rule for that that would keep me from writing all this junk out? So if the power on the top is smaller than that, or the power on the bottom is bigger than that, either way, y equals 0, you're done. So it's really easy to find the horizontals. Power is bigger on the bottom, it's always y equals 0. Power, highest power, same on the top and the bottom, y equals the coefficient divided by the coefficient. And when the power is bigger on the top, what do you have to do? Do the division. Whether synthetic or long, it's up to you on what you're able to, or up to the problem, what you're able to do. And then whatever you get, just toss that remainder and be done with it. So that is my hope. And if you forget all that stuff, check it out. How do you find, if you move over to the next page, how do you find horizontal asymptotes? Right here. Look, if the power, the n is the power on the bottom. If the power is bigger on the bottom, you always get y equals 0. And by the way, don't say 0. Say y equals 0 because it's a line. Okay? If the powers are the same on the top and the bottom, it's always y equal top coefficient over bottom coefficient. Done. You don't have to do any division. And if the power on the top is bigger, that's when you don't have a horizontal. What do? You divide to get the slant. So how do you find a slant? When the top power is bigger, do the division, toss the remainder, or go back and look at the notes on slant asymptotes. And again, set it equal to y because it is an actual line or curve. Are y'all with me on this? So right now you should be able to find horizontals or slants. Now, there are not both. On any one rational function, you can't have a horizontal and a slant. Think about it. I just said that a slant or a horizontal determines end behavior, right? How could I possibly have a graph, say, with that horizontal and that slant? I can't follow it up there and follow it out there. Or it would be a what? Or it wouldn't be a what? It wouldn't be a function. I can't do both. So you won't have both. Now, there are some weird functions that we hit in calculus that as you go to the right, it'll be a slant. As you go to the left, it'll be a horizontal. Or as you go to the right, it'll be this horizontal, and the left is that horizontal. We will not see that this year or next year. Okay, well, maybe very, very end of next year, possibly. But you're not going to have both. It's going to be one or the other. All right, and it makes sense too if you look at these rules right here. The powers, it is all about the powers. So right here, it's either that, or that. You can't be bigger on the top and be bigger on the bottom. It's one or the other. So decide what it is. If it's the top two, you got horizontals. If it's the bottom, it's a slant. Okay, now, with that in mind, what about the rest of this stuff? So I'm going back up to the beginning of this, and I'm giving you an example function. I want to walk through it with you. And then if we can, we'll do a couple problems and probably have a really, really super light homework night if you want to work on some other things. So looking at this function, I was kind enough to factor it for you. I'm not going to, on your test, give you some big function that require you to do some really ugly factoring, maybe a trinomial, maybe a binomial, but nothing like this where you might have to pull out your possible rational roots and check with synthetic division. We're not doing that in here, okay? So if I gave you something this big, I would also give it to you fat. Now, right here, are you able to look at this original function and tell me whether this has a slant or a horizontal. And if so, what it is. Why?
Because the powers are the same.
Highest powers are the same. So what would that horizontal be? Y equals 2. Is everybody able to see that? So from that, you would look at it and you go to y equals 2 and you draw a dotted line on the graph. You already know that this graph is going to head that way and that way at y equals 2. What's going to happen in the middle? We got to figure out. But on the ends, it's going that way. Okay, now, what if I didn't give it to you like this and I gave it to you like this? Are you able to tell that the powers are the same? Can you see that? You can look at that and go, oh yeah, because if I were to FOIL this out, that would be x squared x cubed with a bunch of junk times 2x cubed. This would be x times x times x and a bunch of junk, x cubed. Are y'all able to see that it would still be y equals 2 from that? And be careful, because sometimes I'll have like a 3 in there and like a 5 in there. I mean, really look at it. X, that's 3x squared times 2. That would have been a 6x cubed, or 3x cubed. And this would be x, 5x, x. That would be a 5x cubed on the bottom. So be careful that you take a good look at it and don't get sloppy. All right. Now, what else do you notice about that factored expression that's maybe jumps out at you a little bit? Anything? You got an x minus 2 on the top and the bottom? What do you generally do on a fraction when you see it on the top and the bottom? You cancel it out. Now, if I cancel it out, that doesn't mean that it's not still in the function. And clearly, if I plugged a 2 right there and right there, what do I get? 0 on the top and the bottom. So what that means is if I asked you on this function to find f of 2, I can plug it in there, I'm going to get a 0. I can plug it in there, I'm going to get a 0. That's undefined. What do you think that tells you about your function? There's nothing there at 0. But there's a special nothing there. It's not a vertical asymptote. That's another nothing there on a function. If you look up here and you see that something cancels like this, and there could be more than one, there's just not one here. If it does, this represents a hole in the graph. Now again, a hole in the graph is different from a VA. A vertical asymptote, as the graph gets closer, it either shoots up or shoots down. And then from the other side, it either shoots up and shoots down. Can't cross it, but it's going to do like that, or maybe like this, or like this. A hole is a point on the graph that it goes in one side, comes out the other. Now, what I know from this is that my hole has an x value of, anybody? 2. Kind of like you did, set it equal to 0 and solve. The hole has an x value of 2. But I need to know the y value that goes with it. How do you always find y values if you know x values? Plug it back in. Now, if I plug it back in here, what do you think you're going to get? 0 over 0. Why? Because those two factors are in there. So if you want to find the y value, don't plug it in here. Try it. You'll get 0 over 0. You eliminate these and never look at them again. By the way, they are literally useless for everything other than finding that 2. But now that they're gone, if I plug a 2 in here, I get what? 2 times 3 times -1. So -6. Plug it in there, I get 4 times what? 1, which is 4. So my hole ends up being 2 comma -3 halves. So what would I do? I would go over to 2, down 1.5, and instead of marking it as a point, I mark it like an open circle. The graph is going to go in that open circle on one side, out the open circle on the other. And if I tried to graph this on my calculator, you will not see a hole. On some really old calculators that have giant pixels, like the 84s, you guys don't buy an 84, buy an Inspire, but you'll never even see it. But if I went to trace, and I went to that value, you'd see when x is 2 and there'd be a blank for the y, there'd be nothing there. All right? Please get rid of your holes. You're going to see in a second, if I don't get rid of the holes first, then when I go to do vertical asymptotes use the denominator. You're going to think that represents a VA. When I go to do x-intercepts come from numerators. You're going to think that represents an x-intercept. And your whole graph is going to look like crap, and you're not going to be able to make sense of it. So the first thing you do, no matter what, once you get it factored, find your whole X value, cancel it out, plug it back in everywhere you can, find that, and never look at that whole value again. Are we good? Okay, so at this point, we should have horizontal asymptotes, or maybe a slant, and a hole. Now, what else can I get out of this? So we've done this part, holes, we've done horizontals, and we've done slants. Now let's move to vertical asymptotes. Vertical asymptotes are the other places where the graph doesn't exist. Where do places not exist? When what? The zero in the denominator, right? So I look back at my denominator. Check it out. I'm looking back at my denominator. And when I look back at this denominator, remember, I've already canceled that. I have already canceled out my holes. So I look back at this and I go, oh, right here and right here, those X values represent vertical asymptotes. So all I do is set that equal to 0 and solve, set that equal to 0 and solve. And these will be two vertical lines, one at x minus x equals -2, one at x equals 1. You'll put those dotted lines in there along with your horizontal asymptote. And now you'll have all of your, or your slant, you'll have all of your asymptotes. You have all of those guiding forces that draw graphs to itself. Are you with me so far? Now, the last two things I think you can get out of this are pretty easy to find, so we find them. And they are, and by the way, if you forget that, go look, vertical asymptotes. To find them, set what is left of the denominator after canceling out the holes. Set what is left equal to 0 and solve. Those are your verticals. You got to cancel out the holes first, or you're going to think you have an extra vertical asymptote. All right, last thing, last couple things. X-intercepts. Now, how do you typically find an x-intercept? You plug it, set y equals 0. Plug in 0 for y. Now think about it. I'm just going to give you a random fraction. Back up to the top here. Look what happens right here if I set y equal to 0. Check it out. If I plug a 0 right here, what would you do to solve? What would be the first thing you did? Heck, I'll make it easy. What if I had something like this and I said solve? What's the first thing you do? Multiply both sides by an x plus 5 to get rid of that? What happens when you multiply both sides by an x plus 5? That stays 0 and that just goes away. So what matters? The numerator. So if I want to know x-intercepts come not from there. This is what's giving me VAs and holes, right? Ignore all that. Look at what's left. So whatever is left here that has an x in it, those spit out x-intercepts. Guys, make sure you kind of imprint your brain with the knowledge that you don't, these aren't suggestions. These are, hey, here are the couple of the x-intercepts. There's a lot of super secret hidden x-intercepts out there. This is it. This one only has 2. Sometimes there's only 1. Sometimes there's 4. Okay, go with me? Okay, so those are the only x-intercepts you have. It's going to be very tempting when you sketch your graph to go, man, I really feel like it should cross here. But if there's not a point mark for an x-intercept, you won't be able to cross. So don't go, oh, it really looks like it should do this. It feels like it should do it. If you don't have an x-intercept there, you can't cross. It must not cross the x-axis. It must shoot up another direction. You've got to make sure that you're careful about that. And then the very last thing I want to talk about is y-intercepts. Well, if you plug a 0 in for y to find an x-intercept, what do you do to find a y-intercept? 0 in for x. Now look how easy this is. If you have half the original function, plugging a 0 in for x just makes anything with an x go away. And what are you left with? Y equals 3. So your x-intercept, I'm sorry, when you plug a 0 in, y-intercept, when you plug a 0 in for x, the y value is 3. Now, if you didn't have that, it's not as easy, but it's still not bad, right? If I plug a 0 in for x here, what do you end up with? I mean, obviously it's going to be 3, but you get 2 times 1 is 2, times -3 is -6, times -2 is +12. And then you get 2 times -1 times -2, which is 4. So you might have to do a little work to get your 0, 3. But either way, I can find my intercepts that way. And at that point, you'll have your slants, your horizontals, your verticals, your holes, your x-intercepts, your y-intercepts. You'll have so much information on your page that you probably have enough to do a decent sketch. And if you don't, then we'll plot an extra couple points. You're struggling. All right, so let's just take a look. Sleepy folks in here. I'm on the classwork practice. We'll probably only have a chance to do one of these. All right, so if we have this next one left, do it on your own. But I'll walk you through this. Let's go step by step. Now, what's the most important? Well, first of all, it's not even factored, right? So I probably want to factor it to be able to get any of this done. If I really wanted to, I could certainly find my horizontal asymptote. That's pretty easy, but I'm going to go ahead and factor it right here. And by the way, if you can't factor it, you probably want to work on that. I know some of you think you can, but you really are kind of weak. You need a little help. First step to recovery is admitting you have a problem. Come in here in the morning, Mr. Hurry, I sneak it back. I had a kid I taught for 3 years as calculus, and I was like, guys, we got to know how to factor. Anybody struggling? It's the kid from the back. Yeah, I can't factor. He came in, and when I explained it to him as a senior or whatever, he was like, oh, it must have been some Pavlovian reaction he had in 7th or 8th grade that kind of held him back. But if you just give me a little one-on-one, the factoring is not going to be as bad as your factoring test, but make sure you know how to factor stuff. Okay, so from this, just looking across here, what do we see? Anybody? There's a common x plus 2, right? So I use that to find the x coordinate of my hole, -2, and I will never look at that again for any reason whatsoever. It is useless after this. So what is the y coordinate of my hole? Plug that back in. -9 over -1, so 9. Sorry, my graph does not hold that, but we're still going to mark that as a point, a hollow point, basically a hole. So you do an open circle for that. -2, 9. Done with holes. Now, can you tell anything about vertical asymptotes? They are what? Take the what? What's left of the denominator, this vertical, right? Takes whatever's left of the denominator, set it equal to 0. So x equals -1. Well, I can come in here and I can graph that vertical line, x equals -1. Got that in there? Can I find a horizontal or a slant? Which one does it have in this case? Horizontal. Now, I could look at the original problem and see that because the powers are the same. So what is the horizontal? What? Y equals 1, right? Don't just say 1. So the horizontal is y equal 1. I could also have looked at this part right here and seen 1x over 1x is y equals 1. And if it has a horizontal, will it have a slant? No. So there are no slants. You can only have one or the other. And I can mark that in here. Y equals 1. It'll follow that up. Now, can I find x-intercepts? Where do we say x-intercepts came from? Any value with an x in it in the numerator, if there's a constant, I can ignore that. I say, all right, set that equal to 0, and I get 7. And what's the y value? 0, because remember, I'm plugging a 0 in there. I can mark the point 7, 0, and that represents the only time you cross the x-axis. There are no other ones that you just don't know and that might show up later. That's it. Okay, and then what about y-intercepts? Plugging in 0 for x here gets rid of everything but what? -7. Or plugging a 0 there gives you -7 over 1, which is -7. So I'm going to mark 0, -7. Now, I have enough right now to sketch this, but it wouldn't be a great sketch. So another thing I tend to do is say, hey, plot at least one point on either side of the vertical asymptote. Just get an extra little piece of information. I on a test would have given you this table, and I'll tell you which ones to plot. I'm going to plot -4 for x on this side, and over there I'm going to plot +3. So what happens if I plug a -4 into this function? And again, I don't have to use the original one. I don't even have to think about the x plus 2's. I can just plug it into that. So what do I get here? -11 over -3. So what's a -11 over a -3 about? First of all, it's positive, right? About 3 2/3. So 3-ish. So at -4, I'm going to go up 1, 2, 3-ish, and I'm going to mark a point there. And then if I plug in +3, I get what? -4/4. So -1. So those are the 2 points that I got out of that. So I'm going to go to +3, -1, mark that point there. Now, have you ever taken a multiple choice question or multiple choice test and you have no idea what the letter or the word or the phrase in say B means, but you know it ain't A and you know it's not C and there's no way it's D or E. So you're like, I don't even know what that letter stands for, but I've eliminated everything else. I'm going with it. We've done that, right? When you go to graph these, there are going to be many times where you're going, how do I know what to do? And it's sometimes not as much about what you know you can do about knowing than it is about knowing what you can't do. Okay? Now, there is some knowing what you can do. Like, for instance, what does a horizontal asymptote or a slant asymptote do? It tells you what? What the graph does as you go what? Get further away. So why don't I start with that? I'm going to start way out here. So what this means is, as I'm way out here, what should I be really, really near to? The horizontal asymptote. So that means I have to come in along this line. Now, once I come in, what do I now have to do? I'm going to have to go down because I have to cross this. So if I am currently on this horizontal and then I have to cross this, I'm going to go through that. And then what am I going to have to do? Go through that one. And then what do I have to do? Go through that one. And by that point, what are my only options? Can I cross the VA? That's the only asymptote you can't cross. At that point, I've got to go down. So this thing is going to be actually a lot smoother than I'll probably draw it, but it actually does this very smoothly. If you're not super smooth, I don't care, as long as it's not wanky and janky, but it's going to do this and cross. Now I have a question. What's to keep this graph from coming down here, hitting that point, turning around, and shooting up? It's a VA. There's not. And you're allowed to cross a horizontal. You just can't cross a vertical. There's not another x-intercept. That's the only x-intercept. For me to do that, what did I have to do? I had to cross the x-axis. And I'm not allowed to cross the x-axis. So I can't do that. And if I can't do that, what am I left to have? Hit this and shoot downward. Are you with me on that? Those are my only options. Now, what has to happen as I head to the left? Got to follow the slant of the horizontal. So here I am coming along this horizontal. What are my options? Tell me why I can't go down. Even if these two values were not written, why can I not go down? There's not another x-intercept. Look, even if I don't even have those, I cannot go down because to do that, I would have to go from a +1 through the x-axis and then downward. I can't. There's no place to cross. There's like no bridge there. X-intercepts are bridges across. So what does that mean? Then I must be really close at some point, but then just turn and head up, go right through that hole. Now, why can't I hit that hole, suddenly turn and go down? There's not another x-intercept. And by the way, why can't I just stop? First of all, these curves don't stop. The only places that can't exist for x are at -1 and at -2. Everywhere else, there has to be a point. So that means I'm going to have to get infinitely close to this asymptote. Because the only place I can't plug something in is at -2, -1. Everything else goes. Are y'all seeing this? Now, a couple other things before what time do we have? Oh, we got 5 minutes. Jump to this next one. real quickly. Let's see if we can sketch all that, do all this. Holes. What do you know about holes? What do you see? At what? At -2, right? Common factor. At -2, there's a hole. I don't ever want to look at that again. What's the y value of the hole? Well, let's see. -2 minus 1 is -3. -3 squared is 9. -2 minus 4 is -6. -2 minus 3 is -5. -5 squared is 25. What do I get when I take a -54 and put it over a 25? First of all, that is my hole. But how would I graph that? I would go down what? A little more than 2-ish. So -2-ish. So at -2, I go down to about -2-ish and I put a hole. That's good enough for me. VAs. Do I have any VAs? You see them? Denominator. So x equal +3. I'll talk about that squared in a second. VA. Do I have any horizontals? Can you look at this and tell me what the horizontal is? Talk to me. What would I have had on the top? X to the what? Well, you can even look after you cancel. It's okay. I would have x cubed left on the top. What on the bottom? X squared. Is there a horizontal? No. So I would actually have to multiply all that out. And if I have a higher power on the top, what does that mean? There's going to be a slant. So I would have to go find that slant. Now, granted, I don't know why I did that to you. I would have to FOIL all that out, do that, and do long division and get it. We're not going to have time for that problem. I want to talk about a couple other things. So there will be a slant. I don't know what it is right this second, but I'd have to go find it. Are you with me so far? What are my x-intercepts? X would be what? 1 or 0 and 4 or 0? And what about y-intercepts? I'd plug a 0 in for x, right? And I'd get 1, -1 squared, which is 1, -4 on the top, -3 squared, which is 9. What does that tell me? Maybe close to -0.5. So I've got a point at 1. I've got a point at 4. I've got a point at -0.5. And I've got a slant somewhere in there and I have to go back and find. Now, this is what I wanted to talk about before this bell rings. What does this mean? Now think about it. What did I get out of x minus 1 squared? I got a root. If that value, that root is squared, what does that tell you here? It bounces. It does not cross. It bounced because it was a double root. That tells me that when I go right here at 1, this thing is going to bounce off the x-axis and head back down. Looking right now, it kind of looks like it cruises up, doesn't it? But because it bounces, I bounce where it's at 1 and goes back down. But I'm definitely crossing at 4. Now, another thing. What do you think this means? Anybody gets this, they get the gold star. Huh? What does that square on that value give me? Now, that led me to what? That VA, right? Let me give you a hint. Do y'all remember this curve from Helmer's class? What was that? Y equals 1 over x squared. Somebody.
Oh, wouldn't this like perpetually close?
Anybody that we called it, it had a name. The volcano graph. You ever did the volcano? If you didn't, don't worry about it. 1 over x squared is a volcano. 1 over x does this. 1 over x squared does this. When you see a squared in a denominator, that means the asymptote will head both up or both down, or any even power. When it's not squared, like the last problem we did, it always goes in different directions. That's a huge hint. So if I see a VA that's not squared, it didn't come from a squared factor, then I know it's going to do this. But if it comes from a squared factor like this one, I know it's going to do this or this. We'll finish this up tomorrow. Don't even bother trying. I mean, if you want to multiply that out, you can. But we'll add and pile onto this tomorrow and kind of finish most things up. And if you haven't worked on that state test, you can start working on that a little bit more tonight. Look. No, no, it's turning. There's that next out right there. It gives you the schedule. I think it's Monday, Friday. I think it's in this. Parker room. Monday, Friday morning at 7. If you're not up that early. Media center. 3. Yeah, just start it out. I'll figure it out. Yeah.
I was thinking about it, I think I'll be able to manage it if I just do math next year again.
Yeah, well, you got time. Like you keep rolling like you're rolling, you're in good shape. So
I'm feeling pretty good about it, so I'll probably do it next year.
so guys,
What's up?
how's life treating you? Good day today? Mostly? I'll take mostly. Mostly good is pretty good. So, man.
I'm sorry, Dahlia, my phone's
I literally almost picked it up. I was like, oh, I'll just text her. Oh my God.
What?
Hmm.
Yeah. Got an 89 on
Hmm.
the test.
What test we talking about? Oh, I missed one.
Did you get 100, JW?
Got 89.
Yeah.
I got friggin' 8.
There's B and R. JW got an 89?
Bro, what the heck was the most question?
No.
No, I bet it was
You
better.
better lot better than that.
No, I bet it was the
I'm
calculator.
dummy.
Big guy pulled out the A.
Boom!
Point out that's
Oh my gosh.
that was the calculator part that messed me up. Wait, what's the calculator?
I don't even remember. I'll hand him out.
What's the calculator part that messed me up? Or was it the graphing photograph?
I don't remember because I graded so many. But
Boom. That's a moment to remember.
Best day.
A good test day, dude. Those psych tests are.
Oh, I did not good on that.
How hard is Spanish 3 compared to Spanish?
Oh my gosh.
Oh my God.
So much harder.
Really?
Yeah. It's
So much more application to Spanish in your speech and writing.
Yeah.
I think I missed a question because one of the questions had about a last day. I had no idea what last day was.
Well, I mean, you could like tell what the question meant, just like based on the context.
What? I got 86. I got 70, dude.
Was that Spanish or the?
Since Sunday night, my grade in Spanish has dropped 8 points.
Was that a 3 AP?
Yeah.
Gosh, I didn't even get a 4 on the meeting.
Nope.
Yeah, 74 in Spanish right now.